Imagine you possess a ship that never runs out of fuel and a map of every habitable world in the Milky Way. You leave Earth today, determined to set foot on all of them. It sounds like the ultimate adventure. But as you jump from star to star, something terrifyingly beautiful happens. You realise that this journey is longer than the history of our species. By the time you're halfway through the list, Earth will have forgotten your name. By the time you finish, the constellations in the sky will have completely changed. We are going to simulate this impossible voyage across the galaxy. We will explore the strange landscapes of worlds waiting for life and discover exactly how many eras of time you would need to claim the galaxy as your own. Also, how many alien civilizations are we going to find? Let's find out. If you are ready for the longest road trip in history, hit that like button and subscribe, and tell me in the comments, which planet would you visit first, Mars or an unknown world in deep space? Now settle in, relax, we begin. To understand the length of this journey, we first have to understand the map. The human mind is not built to understand the galaxy. We evolved to understand the distance between the cave and the river, or the hunter and the prey. We measure distance in steps, in kilometers, in days of travel. But the Milky Way laughs at our measurements. It is a disk of starlight and dust 100,000 light-years across. That number is easy to say, but impossible to feel. So let us turn the galaxy into something you can hold. Imagine the sun is a grain of sand, a single, tiny grain of silica. On this scale, Earth is a microscopic speck of dust floating an inch away. Now, where is the next nearest star, Proxima Centauri? If the sun is a grain of sand in your hand, Proxima Centauri is another grain of sand about 4 miles away. The space between them is not empty air. It is a vacuum so perfect and so wide that the human mind slides off it like water off glass. Now, fill a hall with sand, fill a stadium, fill a city. That is the galaxy. It is a blizzard of stars separated by screaming silence, and hidden within that blizzard are the prizes we seek, the habitable worlds. For a long time, we thought these worlds were rare. We thought our solar system was a lucky roll of the cosmic dice. But we were wrong. We have stared at patches of the sky no bigger than a thumb held at arm's length, and we found thousands of planets. We found gas giants roasting near their stars, and ice worlds frozen in eternal night. But we also found the rocky ones, the wet ones, the ones that sit in the warmth. Based on what we know today, there could be 300 million worlds in our galaxy capable of holding liquid water, 300 million oceans, 300 million sunrises. If we distributed them evenly, the nearest one might be right next door, just 4 light-years away. But the galaxy is not neat. It is a chaotic, swirling structure. Some of these worlds are clustered in the bright, deadly core. Others are drifting alone in the dark outer rim. Our mission is to visit them all, not just to look at them through a telescope, but to orbit them, to send a probe into their atmosphere, to plant a flag, literal or digital, that says we were here. This is not a trip for a weekend. It is not a trip for a century. The sheer geometry of the Milky Way dictates that this journey will take longer than recorded human history. To solve this problem, we cannot just look at rockets. Rockets are toys. Burning chemical fuel to cross the stars is like trying to cross the Pacific Ocean by throwing rocks behind you. It does not work. We need new physics. We need to bend light, ride nuclear shockwaves, and perhaps even eat the interstellar medium itself. But even with the best engines physics allows, the clock is our enemy. As we travel, the galaxy will move. Stars will die and turn into white dwarfs. Nebulae will collapse into new stars. The map will change while we are driving across it. We are not just travelling through space, we are travelling through deep time. The silence of the galaxy is heavy. It presses down on us. It begs the question, if there are 300 million stages for life to act upon, why is the theatre empty? Why has no one else done what we are about to do? Perhaps the distances are just too great. Perhaps the void is a prison cell that no civilization can escape. Or perhaps they are waiting for someone to take the first step. We are that someone. The ship is ready. The course is plotted. We are starting from Earth, a blue marble fading in the rearview mirror. Our first destination is the Alpha Centauri system, the gateway to the rest of the galaxy. It is the closest shore to our own. But even this short hop, this microscopic jump on the galactic map, will force us to confront the tyranny of the rocket equation. We are leaving the cradle. We are stepping out of the nursery and into the dark forest. It is time to see how big the universe really is. To understand why this journey is so hard, we have to look at the engines we use today. When we see a rocket launch, we see power. We see fire and noise shaking the ground. We see a machine piercing the sky. It feels like triumph. But to the galaxy, a chemical rocket is not a roar. It is a whisper. We have built fast ships before. The Voyager probes are currently falling away from the sun faster than a bullet. They cover 17 kilometers every single second. At that speed, you could fly from New York to London in 5 minutes. But on the scale of the Milky Way, Voyager is not flying. It is standing still. If Voyager was aimed at our nearest neighbour, Proxima Centauri, it would not arrive in our lifetime. It would not arrive in the lifetime of your great-grandchildren. It would drift through the void for 70,000 years. 70,000 years ago, humans were just learning to paint on cave walls. That is the timescale of chemical rockets. They are too slow, and the reason they are slow is a trap hidden in the laws of physics. Engineers call it the tyranny of the rocket equation. It is a curse that haunts every launch pad on Earth. The rule is simple and cruel. To move a ship, you need fuel, but fuel is heavy. It has mass. So to lift that fuel, you need more fuel, but that extra fuel also has mass, so you need even more fuel to lift that fuel. It is a vicious cycle. It is an exponential spiral of weight. If you want to go just a little bit faster, you do not just add a little bit more gas, you have to double the size of your ship. If you want to go twice as fast, you might need a ship the size of a mountain. Think about the Saturn V that took us to the moon. It was a skyscraper filled with explosive liquid. But the part that actually came home, the tiny capsule with the 3 astronauts inside, was the size of a minivan. Everything else, 90% of the rocket, was just fuel burn to get that minivan off the ground. Chemical energy is weak. It is just the breaking of electron bonds. It is the same energy released when a log burns in a fireplace. Trying to cross the galaxy with chemical rockets is like trying to drive around the world using a car that burns a tank of gas every 10 feet. You would have to tow a fuel tanker behind you, and a tanker to fuel the tanker, until your caravan stretched across the horizon. We cannot conquer the galaxy with fire. The distances are too vast and the chemical bonds are too weak. The void between stars is an ocean, and we're trying to cross it in a canoe. If we want to reach those 300 million habitable worlds, we have to stop thinking about fire. We have to start thinking about the forces that bind the universe together. We need engines that do not just push. We need engines that scream. But before we build them, we must understand exactly where we're going. We need to look at the first stepping stone, the system that sits right on our doorstep, tantalizingly close, yet effectively unreachable. This is the Alpha Centauri system, and hidden in its red glare is the first world on our list. When we look for a place to land, our eyes turn first to the constellation of the Centaur. There, shining brightly in the southern sky, is a star that looks like a single point of yellow light. But that is a lie told by distance. If you could fly closer, that single point would split apart. You would not see one star, you would see 3. This is the Alpha Centauri system. 2 of them are giants, sun-like stars locked in a gravitational dance, swinging around each other like dancers holding hands. But the third one is different. Drifting far away from the main pair is a small, dim, red star. It is invisible to the naked eye from Earth. It is a cosmic ember, burning slowly and coldly. We call it Proxima, and orbiting this red ember is the closest habitable world to Earth. We call it Proxima b. It is a world slightly heavier than our own. It sits in the warmth, just close enough to its star that water might flow on its surface without freezing or boiling away. It is the first prize in the galactic lottery, a potential second home sitting right on our doorstep. But doorstep is a dangerous word. It implies you can just step over the threshold. In space, a doorstep is a gulf that defies imagination. Proxima Centauri is 4 light-years away. To a physicist, that sounds short. It is just down the street. But let us translate that into human terms. Imagine you could get in a car and drive to Proxima b at highway speeds. You drive without stopping. You drive past the moon, past Mars, past the edge of the solar system. You keep driving for 1 million years, then 10 million years, then 40 million years. You would still be driving. That is how far next door is. Even light, the fastest thing in the universe, takes 4 years to cross this gap. When we look at Proxima tonight, we are not seeing it as it is now. We're seeing it as it was 4 years ago. We are looking into the past. If a civilization on Proxima b turned on a flashlight aimed at us right now, we would not see it until 4 years from now. We are separated by a wall of time, and this is just the closest star. Remember, we want to reach every habitable planet. We want to reach the ones on the other side of the spiral arms, thousands of times further away. If Alpha Centauri is a grain of sand 4 miles away, the rest of the galaxy is a beach stretching around the world. But let us assume we get there. Let us assume we build a ship that can cross the void. What awaits us? Proxima b is not Earth. It is an alien rock. Because its star is so dim, the planet has to huddle close for warmth. It orbits closer than Mercury orbits our Sun. Because it is so close, gravity has likely locked it in place. One side of the world faces the star forever, in an eternal scorching day. The other side faces the frozen blackness of space in an eternal night. Life, if it exists there, would live in the twilight strip between the fire and the ice. It would grow under a red sun that never sets, in a world of constant winds rushing from the hot side to the cold side. This is the reality of the habitable zone. It is not always a paradise. Often, it is a precarious edge where life hangs on by a thread. To reach this twilight world, we have to solve the problem of speed. We have to break the tyranny of the rocket, and the first way to do that is to stop carrying our own fuel. Instead of pushing ourselves, we need to let the universe push us. We need to learn how to sail on light itself. When astronomers announce the discovery of a new habitable world, the headlines always paint the same picture. We see artist illustrations of blue oceans, fluffy white clouds, and green continents. We imagine a second Earth, waiting for us to arrive and plant our crops. We call this the Goldilocks zone. Not too hot, not too cold, but just right. It sounds cozy. It sounds like a fairy tale. But the universe does not tell fairy tales. The Goldilocks zone is a lie of omission. To an astronomer, habitable is a very simple thermal calculation. It just means a planet is at the right distance from its star so that water, if it exists, would not instantly boil into steam or freeze into ice. That is it. It does not mean the air is breathable. It does not mean the gravity will not crush you. It does not mean the planet is alive. Think of our own solar system. We have 2 neighbours that sit right on the edges of this zone. Mars is the frozen desert. It has the land, but its atmosphere was stripped away billions of years ago, leaving it naked to the radiation of space. If you stood there without a suit, your blood would boil, and you would freeze at the same time. Then there is Venus. It sits just inside the inner edge of the zone. It is a planet the same size as Earth, made of the same rock. But Venus is a pressure cooker wrapped in clouds of sulfuric acid. The surface is hot enough to melt lead. It is a hellscape, yet it sits right next to the paradise of Earth. Distance is not enough. To build a home, you need more than just the right seat by the fire. You need a shield. Earth has a molten iron heart that spins deep underground, generating a massive magnetic field that stretches out into space. This field is invisible, but without it, our atmosphere would have been blown away by the solar wind eons ago. We would be as dead as Mars. When we look at those 300 million habitable worlds, we have no idea how many of them have this shield. We might fly for 1,000 years to reach a blue planet, only to find it is a water world with an ocean 100 miles deep. On such a world, there is no land. The pressure at the bottom of that ocean would be so intense that water would turn into a strange solid ice that is hot to the touch. It would seal off the minerals below, preventing the chemistry of life from ever starting. Or we might find a super Earth, a rocky giant with gravity so strong that we could barely stand up. The atmosphere might be so thick it crushes our ships like soda cans before we even touch the ground. These are the trickster worlds. From a telescope, they look like home. Up close, they are traps. So when we say we want to visit every habitable planet, we are not planning a tour of garden worlds. We are planning an expedition into the unknown. We are looking for a needle in a haystack, but the haystack is made of poison, ice, and fire. We are looking for the rare combination of water, rock, shield, and air. And to find that combination, we have to cross the emptiness. We have to leave the warmth of our sun and enter the space between. This is the part of the journey that frightens us the most. It is not the destination that breaks the human mind. It is the journey through the nothingness. We have talked about the islands. Now we must talk about the sea. To reach the next star, we must cross a region of space so empty that the human mind struggles to comprehend it. We call it the interstellar medium. It sounds technical, like a fluid or a gas. But to a traveller, it is simply the ocean of night. Imagine you're on a ship halfway to Alpha Centauri. You look out the window. Behind you, the sun has shrunk. It is no longer the burning furnace that defines your days and nights. It is just the brightest star in the sky, a cold pinprick of light indistinguishable from Sirius or Canopus. You have lost your anchor. For the first time in human history, there is no down, no up, no morning, and no evening. There is only the ship and the silence. This silence is heavy. On Earth, silence is just a pause in the noise. In the void, silence is the default state of the universe. It is a silence that has lasted for 13 billion years. The space outside your hull is not completely empty, but it is close. On Earth, the air you breathe is crowded. In every sugar cube-sized pocket of air, there are billions of molecules bouncing off each other. In the ocean of night, in that same amount of space, you might find a single atom of hydrogen, maybe two. It is a vacuum more perfect than anything we can create in our best laboratories. Because there is nothing there, there is no temperature. You might think space is cold, and you are right, but it is a strange cold. If you stuck your hand out of the airlock, it would not instantly freeze like in the movies. Heat needs matter to carry it away. In the void, your heat has nowhere to go. You're an ember in a thermos. You would eventually freeze, radiating your warmth away as infrared light, but it would be a slow, lonely cooling. But the emptiness is not peaceful. It is pierced by invisible bullets. Cosmic rays, shattered fragments of dead stars, scream through the dark at nearly the speed of light. They tear through metal. They tear through DNA. On Earth, our atmosphere and magnetic field act as a thick blanket protecting us. Out here, the blanket is gone. The ocean of night is radioactive. This is the psychological barrier of the journey. It is not just about engineering, it is about sanity. Generations of humans might live and die in this void, travelling between the stars. They will be people who have never seen a blue sky, never felt rain, never stood on solid ground without magnetic boots. Their entire universe will be the hum of the air scrubbers and the cold light of the displays. To survive this, we cannot just drift. Drifting takes too long. If we drift, the radiation will sterilize us, or the darkness will break us. We need to cross the ocean quickly. We need to turn the journey from an era into a mission. We need speed. We need to stop crawling and start flying. And to do that, we have to abandon the fire that brought us to the moon. We have to look for something faster. We have to learn to ride the light itself. The problem with rockets is that you have to carry the fire with you. But what if we left the engine behind? What if we could build a ship that is nothing but a sail and let the universe itself blow us across the void? It sounds impossible. We are taught that light has no mass. It is just energy. A flashlight beam does not knock you over. Sunlight does not feel heavy on your skin. But physics tells us something strange. While light has no weight, it has momentum. Every single photon that strikes a surface gives it a tiny, microscopic kick. It is a ghost of a push. But if you have enough light and a big enough surface, that push adds up. This is the dream of the solar sail. Imagine a ship that looks like a giant mirror. It is miles wide, a shimmering sheet of silver foil thinner than a soap bubble. It unfurls in the silence near Earth, catching the full glare of the sun. At first, it moves slowly, painfully slowly. A chemical rocket would leave it in the dust, but the rocket runs out of fuel in minutes. The sail never runs out of fuel. As long as the sun shines, the wind is blowing. Hour after hour, day after day, the light kicks the sail. The ship gets faster and faster. By the time it passes Mars, it is cruising. By the time it passes Jupiter, it is flying. It is the tortoise beating the hare, driven by the relentless pressure of sunlight. But there is a catch. The further you get from the sun, the weaker the light becomes. By the time you reach the edge of the solar system, the sun is just a bright star and the wind dies down. You are becalmed in the dark. To reach the stars, we cannot rely on the sun alone. We have to make our own wind. We call this beamed propulsion. Imagine building a battery of lasers on Earth, or on the moon. A 1 billion-watt cannon of pure light. We aim this cannon at our ship and fire. We focus a beam of coherent light directly onto the sail. Now, we're not limited by the sun. We can push the ship with the power of a civilization. With a powerful enough beam, we could accelerate a small probe to 20% of the speed of light. That is 100 million miles per hour. At that speed, Alpha Centauri is not 70,000 years away. It is 20 years away. We could reach Proxima b within a single human generation, but the violence of this method is extreme. The sail has to reflect almost perfectly. If it absorbs even a fraction of a percent of that laser energy, it will not just melt, it will vaporize instantly. We are trying to push a feather with a blowtorch, and there is another problem. A sail has no brakes. Once you are riding the beam, you are committed. You hurtle through the void at 100 million miles per hour, and when you reach the destination, you zoom right past it. To stop, you would need another laser waiting at the other end to catch you, but no one is there yet, so the sail is perfect for a flyby, a quick snapshot as we scream past an alien world. But if we want to stop, if we want to orbit, land, and walk on these worlds, we need something else. We need an engine that carries its own power, but with a fury that chemical rockets can only dream of. We need to harness the power of the atom. If sailing on light is the gentle way to travel, then our next option is the violent one. To truly conquer the void, we may have to do something that seems insane. We have to take the most destructive weapon our species ever created and turn it into an engine. This is the concept of nuclear pulse propulsion. In the late 1950s, physicists looked at the problem of space travel and realized that chemical fuel was a dead end. They looked at the atomic bomb, which had just terrified the world, and saw something else. They saw raw power. They calculated that if you could harness that explosion, you wouldn't just go to the moon. You could go to Saturn in weeks. You could go to Alpha Centauri in a human lifetime. The design was simple and terrifying. Imagine a spaceship the size of an office building. It is not sleek or aerodynamic, because it never lands. It is built like a fortress. At the bottom of the ship is a massive steel plate coated in oil and graphite. This is the pusher plate. The engine works like a cosmic pogo stick. The ship drops a small nuclear bomb out of the back. The bomb drifts a few hundred feet behind the ship and detonates. The blast hits the steel plate. The shockwave shoves the entire ship forward. Then it drops another bomb, and another, and another. Bang, 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 a rhythmic heartbeat of atomic fire. It is brutal. It is crude. It is like trying to propel a boat by throwing grenades in the water behind you. But the math works. The energy density of a nuclear bomb is millions of times higher than rocket fuel. With this engine, we wouldn't need to count every gram of weight. We wouldn't be sending 3 astronauts in a tin can. We could send 100 people. We could send libraries, hydroponic farms, and heavy equipment. We could build a true explorer's vessel, a ship that could survive the punishment of the deep dark. We actually designed this ship on paper. We built small models that flew using conventional explosives. It was real. We could have been on Mars by 1980. We could be circling Proxima Centauri right now. So why aren't we? Because the price was too high. To launch a ship like this, you have to detonate hundreds of nuclear bombs in our own atmosphere just to get it into orbit. You would leave a trail of radioactive fallout across the planet. You would be poisoning the Earth to leave the Earth. And if the launch failed, if a rocket carrying 1,000 nuclear warheads exploded on the pad, it would be a catastrophe that would end nations. So we signed treaties. We banned nuclear explosions in space. The dream of the pulse drive was locked away in a filing cabinet, a road not taken. But the physics hasn't changed. If we build it in deep space, far away from Earth, where the fallout can't hurt us, the nuclear heart is still beating. It remains the only technology we have right now that could plausibly take humans to another star. However, fission, breaking atoms apart, is messy. It leaves behind radioactive trash. There is a cleaner, more powerful fire, the fire that burns inside the sun itself. If we want to travel like a star, we have to learn to build a star inside our engine. We need fusion, and we need something even rarer, the mirror image of matter itself. If nuclear fusion is the engine of the stars, then antimatter is the engine of the gods. It is the holy grail of rocket science. It is the most potent fuel that physics allows, and it is the most dangerous substance in existence. To understand antimatter, imagine looking in a mirror. You see a reflection that looks exactly like you, but everything is reversed. Your left hand is your right hand. In the subatomic world, this mirror image is real. For every particle of matter that makes up your body, every proton, every electron, there is a twin out there, an antiproton, an anti-electron. They are identical to normal matter in every way, except for their electric charge, but they cannot coexist. Matter and antimatter are cosmic enemies. If they touch, they do not just mix, they annihilate. They cease to exist as solid objects and instantly turn into pure, blinding energy. This is the only reaction in the universe that is 100% efficient. When you burn gas in a car, you are wasting most of the energy as heat. Even a nuclear bomb only converts a tiny fraction of its mass into energy. But matter-antimatter annihilation converts everything. It unlocks the full, terrifying potential of Einstein's famous equation. The power is staggering. If you held a paperclip made of antimatter in your hand and you let it touch the air, the resulting explosion would be larger than the bomb that destroyed Hiroshima. A teaspoon of this stuff could power the entire planet Earth for days, or it could push a starship to 90% of the speed of light. With an antimatter engine, we would not need a ship the size of a city. We could build a sleek, fast vessel. We could cross the Gulf to Alpha Centauri in just 6 years. We could reach the edge of the galaxy within a human lifetime. It sounds perfect. It sounds like the answer, but there is a catch. In fact, there are two. First, antimatter is the most expensive substance in history. We do not find it lying around in mines. We have to make it, atom by agonizing atom, in our largest particle accelerators. Right now, to make just 1 gram of antimatter would cost trillions of dollars and take millions of years. We are currently producing it in amounts so small that we can barely detect it, let alone burn it in an engine. The second catch is storage. How do you hold a fuel that destroys anything it touches? You cannot put it in a tank. You cannot put it in a bottle. If it brushes against the wall of the container, the ship evaporates. To hold it, we have to build cages made of magnetism. We have to suspend the antimatter in a vacuum, floating in the center of a magnetic field, never letting it drift even a millimeter off course. It is a terrifying way to travel. You're riding a ship with a bomb in the fuel tank that is constantly trying to explode. If the power fails, if the magnets flicker for a microsecond, the containment breaks. There is no wreck left to find, just a flash of gamma rays expanding into the dark. Perhaps carrying our fuel is the wrong approach entirely. The void between stars is not truly empty. There is thin gas, dust and hydrogen floating in the dark. What if, instead of bringing our lunch with us, we learn to eat off the land? What if we could scoop up the galaxy as we fly? We have talked about ships that carry their own fire and ships that are pushed by light. But there is a third way, a design that turns the emptiness of space into our greatest ally. The problem with every engine we have discussed so far is the gas tank. Eventually you run dry. But what if the gas tank was the universe itself? The void between the stars is not truly empty. It is filled with a thin mist of hydrogen atoms, the leftover breath of the Big Bang. It is incredibly sparse, just a few atoms in every thimble of space. But over the scale of light years, those atoms add up to an ocean of fuel. This is the dream of the Ramjet. It is a ship that breathes. Imagine a vessel that does not look like a rocket, but like a predator with its mouth open. It does not use a metal intake, because a metal scoop would have to be the size of a continent to catch enough gas. Instead, it casts a net of invisible force. The ship projects a magnetic field thousands of miles wide ahead of it. This field acts like a giant funnel. As the ship moves, it sweeps up the stray hydrogen atoms floating in the dark. The magnetic field guides them, squeezes them, and funnels them into the heart of the engine. There, the pressure becomes so intense that the atoms fuse. They turn into a star. The ship burns the very road it travels on. The beauty of the Ramjet is that it has infinite range. It never stops to refuel. It never gets lighter or heavier. As long as it keeps moving, it keeps eating. It could accelerate forever, getting closer and closer to the speed of light, crossing the galaxy on an endless wave of harvested fire. It sounds like the perfect machine. But like everything in physics, there is a price. The problem is friction. When you try to scoop up the universe at half the speed of light, the universe pushes back. The interstellar medium, usually so thin you can walk through it without noticing, becomes a wall. The same magnetic field that catches the fuel also creates drag. It acts like a parachute. At a certain speed, the drag becomes stronger than the thrust. The faster you go, the harder it is to eat. Some calculations suggest that a ramjet might act more like a brake than an engine, slowing us down rather than speeding us up. We might be building a machine that chokes on its own food. So, we are left with a difficult choice. The fast engines are dangerous, expensive, or theoretically impossible. The safe engines are too slow. We are trapped between the desire to explore and the limitations of our technology. Perhaps we are looking at the problem the wrong way. We are obsessed with speed because we are mortal. We want to reach the stars before we die. But the galaxy does not care about our lifespan. If we cannot build a ship fast enough for a human life, maybe we need to build a life that matches the ship. Maybe we do not need to go fast. We just need to bring the whole village with us. If the laws of physics refuse to let us travel fast, then we must accept the alternative. We must travel slow. We must stop treating the journey as a commute and start treating it as history. This is the concept of the generation ship. It is an admission of defeat, but also an act of supreme hope. It is a ship that is not designed to carry a crew, but a civilization. It would be a hollowed-out asteroid or a rotating cylinder 10 miles long, spinning to create the feeling of gravity. Inside, it would not look like a spaceship. There would be no sterile white hallways or cramped bunks. There would be soil. There would be rivers, forests, and fields of wheat growing under artificial suns. It would be a floating island of Earth, cast adrift in the ocean of night. The people who board this ship will never see the destination. They are the founders. They will watch Earth fade into a star and then into nothing. They will live out their lives in the steel belly of the beast, and they will die there. Then their children will take over, and their children's children. This creates a terrifying human problem. The middle generations. These are the people born in the void. They never chose to leave Earth, and they will never walk on the new world. They are born into a metal prison, tasked with maintaining a machine they did not build, for a purpose they might not believe in. To them, Earth will just be a myth, a story told in the archives. Proxima Centauri will be a dot on a screen that never seems to get closer. Their entire universe will be the ship. The limit of their reality will be the hull. How do you keep a society sane in a bottle? How do you prevent mutiny when the captain is a tyrant and there is nowhere to run? How do you stop them from turning the ship around or simply forgetting the mission entirely? Over 1,000 years, language changes. Culture shifts. The descendants might forget they are on a voyage at all. They might come to believe the ship is the entire universe, and the stars outside are just lights painted on the ceiling. They might arrive at the habitable world and refuse to leave, terrified of the open sky. The generation ship is the most reliable way to reach the stars because it does not require new physics. We could build it today if we had the money and the will. But it requires a sacrifice that is harder than rocket science. It requires us to condemn our grandchildren to a life inside a machine, trusting that their grandchildren will forgive us when they finally step onto green grass. But let us assume we don't want to wait. Let us assume we refuse to accept the slow boat. We want to get there ourselves. We want to beat the clock. To do that, we have to push against the ultimate barrier. We have to confront the one law in the universe that cannot be broken. We have to talk about the speed of light, and why it is not just a speed, but a prison wall. There is a number woven into the fabric of reality. It is the speed of causality. We call it the speed of light, but that is a bad name. Light is just the thing we see moving. The limit itself is deeper. It is the maximum speed at which 2 points in the universe can talk to each other, 300,000 kilometers per second. On Earth, that number feels infinite. You turn on a lamp and the room fills instantly. You talk on the phone and your voice reaches the other side of the world without a pause. But the moment you step into the galaxy, light stops being fast. It starts to look agonizingly slow. If you were watching a ship cross the galaxy at the speed of light, it would look like a snail crawling across a continent. It takes light 100,000 years just to cross our own backyard. To the universe, light is not a sprint. It is a drift, and yet we cannot catch it. This is the central tragedy of space travel. We are trapped by the speed of light not because our engines are weak, but because the universe is stubborn. Imagine you're in a spaceship accelerating. You push the throttle. You feel the G-force pressing you into your seat. You get faster. 50% of light speed, 80%, 90%. You pour more energy into the engines. You should be going faster. But something strange happens. As you approach the limit, the energy you feed the engine stops turning into speed. Instead, it turns into mass. Your ship actually gets heavier. The faster you go, the heavier you become. It is as if the universe is grabbing your bumper, dragging you back. To reach 100% of the speed of light, your ship would become infinitely heavy. You would need infinite energy to move it. There is not enough energy in all the stars of the universe to push a single grain of sand to the speed of light. This barrier is absolute. It means that no matter how advanced we become, no matter how much antimatter we burn, we will never break this rule. We will never be everywhere at once. We will always be lagging behind the view out the window. This limit defines the shape of our empire. It means that the galaxy will never be a single unified nation. If the Emperor lives on Earth, and a rebellion starts on a colony 1,000 light years away, the Emperor will not know about it for 1,000 years. By the time his fleet arrives to stop it, the war will have been over for centuries. The speed of light fractures civilization. It turns the galaxy into a collection of lonely islands, separated by oceans of time that can never be fully bridged. But while the speed of light traps us in space, it does something else to time. As we push against this barrier, the universe begins to bend in strange ways. The faster we move, the slower time ticks. And this leads to the most heartbreaking consequence of the journey. We're about to leave everyone we love behind. We're used to thinking of time as a steady drumbeat. A second is a second, whether you're in London, Tokyo, or on the moon. But Einstein showed us that this is an illusion. Time is not a rock, it is a river. And like a river, it can flow fast in some places and slow in others. The rule is simple. The faster you move through space, the slower you move through time. Imagine you're the captain of a ship travelling at 99% of the speed of light. Inside the hull, everything feels normal. You drink your coffee, you read a book, you sleep for 8 hours. Your watch ticks forward at the same steady pace it always has. You do not feel slow. But if you could look back at Earth through a powerful telescope, you would see something impossible. You would see the planet spinning wildly. You would see seasons flashing by like the frames of a movie on fast forward. You would see cities rise and fall in the blink of an eye. To the people on Earth, you are the one who is frozen. They would see your ship crawling across the sky. If they could see into your window, they would see you moving in ultra-slow motion, taking hours just to blink. This disconnect creates a terrifying reality. If you travel to the centre of the Milky Way, 26,000 light-years away, and you do it at high speed, the journey might only take you 20 years. You would age 20 years. You would have a few grey hairs, a few wrinkles. But when you arrive, 26,000 years will have passed for the rest of the universe. Everyone you knew is dead. The civilization that built your ship is dust. The language you speak might be extinct. You have not just travelled through space, you have travelled through time. You have leaped into the deep future. This means that interstellar travel is a one-way door. You can never go home. Even if you turn the ship around and fly back, another 26,000 years will pass. You will return to an Earth that might not even remember humans existed. The high-speed traveller is a ghost. They exist apart from the history of their species. They are preserved in the amber of speed while the universe ages and dies around them. And yet, this preservation is the only way a human being can see the galaxy. We can visit the edge of the spiral arms. We can see the birth of stars. We just have to be willing to pay the price of never seeing our families again. But there is a more immediate danger than loneliness. As we race through the void at these incredible speeds, the void itself changes. The harmless vacuum turns into a weapon. The softest things in the universe become harder than diamond. We have to talk about dust. We usually think of space as a vacuum, empty, harmless. But when you move at the speed of light, the definition of empty changes. The void stops being a lack of matter and starts being a minefield. Imagine running through a gentle rain. The water is soft, it brushes against your skin. Now imagine running through that same rain at the speed of sound. The water would hit you like gravel. Now imagine hitting it at half the speed of light. The water droplets would not just hit you, they would detonate. This is the kinetic trap. The faster you go, the harder the universe hits you. The interstellar medium is filled with dust. Tiny grains of silicate and ice, no bigger than the smoke particles from a candle. Floating at 0 speed, they are nothing. But when your ship slams into one of these grains at 100,000 miles per second, physics goes crazy. At those speeds, a single grain of sand carries the kinetic energy of a nuclear bomb. If your ship hits a pebble the size of a pea, it is game over. The energy release would vaporize the hull, the crew, and the engines in a fraction of a microsecond. You wouldn't even have time to realize you were dead. You would just turn into a flash of gamma rays, but the pebbles are rare. The real problem is the gas, the hydrogen atoms. There are millions of them in every cubic meter. As your ship plows through them, they strike the front of the hull like a sandblaster from hell. They are moving so fast they strip electrons off the metal. They tear apart the molecular bonds of your armor. If you flew a shiny steel ship to Alpha Centauri at high speed, you would arrive with no ship left. The front would be eroded away, polished down to the frame by the friction of the vacuum itself. So, how do we survive the rain? We build an umbrella. We cannot build the ship like a plane. We have to build it like an arrow hiding behind a shield. The most common design for a relativistic starship is a long, thin needle, thousands of feet long, hidden entirely behind a massive block of material at the front. We might use steel, or Kevlar, or diamond. But the smartest material might be ice. Imagine a cylinder of frozen water, hundreds of feet thick, attached to the nose of the ship. As the dust and gas hit the ice, they blow craters in it. They vaporize it. But that is the point. The ice is sacrificial. It dies so the ship can live. It absorbs the radiation and the heat, slowly boiling away into the dark. By the time we reach the destination, the shield might be half gone, pitted and scarred by the violence of the journey. But the crew behind it will be safe. But even with a shield, the energy cost is enormous. We are spending half our power just to push this dead weight of armor ahead of us. It is another tax the galaxy levies on travelers, and even if we solve the fuel, the time and the dust, we still have to pay the entry fee. We have to slow down, and slowing down from the speed of light is just as hard as speeding up. We have designed the engines, we have built the shields. We have accepted the time dilation, but there is one final hurdle that stops us from leaving the launch pad. It is not physics, it is the bill. Space travel is, at its core, an energy transaction. You are trading energy for speed, and the exchange rate is extortionate. To understand the cost, look at Earth. Look at every power plant, every dam, every solar panel, every gallon of gasoline burning in every car. Add it all up. The total energy output of the human race. It is a staggering amount of power. It lights up the night side of our planet like a Christmas tree. Now imagine we want to send a single ship to Alpha Centauri. Not a tiny probe, but a real ship. A vessel large enough for a crew, with food, water, and air. Let us say it weighs as much as a standard cruise ship. If we want to push that ship to just 10% of the speed of light, a slow, 40-year crawl to the nearest star, we would need to burn energy. How much? To get that one ship up to speed, we would need to consume hundreds of times the total energy output of the entire planet. We would have to turn off every light on Earth, stop every factory, drain every battery, and funnel all of it into the engines for decades. And that only gets us to the neighbour. This is the energy trap. The faster you want to go, the price does not just double, it squares. If you want to go twice as fast, you need 4 times the energy. If you want to go near the speed of light, the cost becomes vertical. To reach 90% of light speed, you need more energy than our sun puts out in a year. This tells us something profound about our place in the galaxy. We are not just limited by technology, we are limited by our budget. Right now, humanity is poor. We are a civilization that scrapes energy off the surface of our planet. We burn dead plants and catch a little bit of wind. To travel the stars, we have to become rich. We have to become a civilization that does not just use energy, but masters it. We need to dismantle other planets for fuel. We need to wrap our sun in solar collectors. We need to harness the power of black holes. Until we can pay the energy bill, the galaxy will remain a picture on a screen. We can send robot probes because they are small and cheap, but sending humans? Sending wet, heavy, fragile biological bodies? That is a luxury we cannot afford yet. So if we cannot afford to go fast and we cannot afford the fuel to push us, we have one option left. We have to change the cargo. We have to turn the crew into something that does not eat, does not drink, and does not age. We have to stop the clock inside our own veins. If we cannot speed up the ship, we must slow down the passenger. The human body is the weakest link in any starship. It is fragile. It requires constant maintenance. It consumes tons of food, water, and oxygen every year. And worst of all, it expires. Our lifespan is a flicker compared to the timeline of the galaxy. If a journey takes 500 years, a human crew is not a solution, they are a liability. Unless we can hit the pause button, this is the promise of cryostasis, the long sleep. It is the idea that we can step into a pod, close our eyes, and wake up 1,000 years later without having aged a day. To the sleeper, the voyage to the stars would happen in a blink. You would say goodnight to Earth, and seconds later you would say hello to a new sun. But biology is stubborn. We are not bears. We were not built to hibernate. We are warm-blooded engines designed to run hot and fast until we die. To stop that engine without breaking it is one of the hardest problems in medicine. The enemy is water. You're made of mostly water, and when water freezes, it expands. It forms sharp, jagged crystals. If we simply froze an astronaut today, the water inside their cells would turn into microscopic daggers. It would shred their cell walls from the inside out. When we thawed them out, they would not wake up. They would just dissolve. To survive the cold, we have to cheat. We have to replace the blood. The process is called vitrification. Before the long sleep, the crew's blood is drained and replaced with a medical-grade antifreeze. This fluid does not freeze into crystals. Instead, as the temperature drops, it thickens. It becomes syrup, then candy, and finally glass. The astronaut is not frozen. They are vitrified. They become a statue made of organic glass. In this state, chemistry stops, decay stops, time stops. A vitrified human could drift through the void for 10,000 years and remain perfectly preserved, waiting for the signal to wake. But the waking is the dangerous part. We have to reverse the process perfectly. We have to warm every cell evenly, flush out the antifreeze, and restart the heart before the brain realizes it has been dead for a millennium. If we get the temperature wrong by a degree, the glass cracks, the memory is lost. If we can master this, the galaxy opens up. We no longer care about speed limits. We can take the slow road. We can sleep through the boredom of the void. But when we finally wake up, rubbing the sleep from our eyes, what will we see out the window? We assume we will find Earth-like worlds, but the galaxy is filled with traps. And the most common type of star in the universe is not like our sun. It is smaller, colder, and far more dangerous. We are about to enter the realm of the red dwarfs. When we imagine an alien sun, we usually picture a yellow star like our own. We assume the galaxy is filled with twins of the sun. But we are the exception, not the rule. The Milky Way is not a yellow galaxy, it is a red one. 75% of all stars in existence are red dwarfs. They are small, dim, and incredibly long-lived. If the sun is a bonfire, a red dwarf is a smouldering coal. Because they burn so slowly, they will outlive every other star in the universe. Long after our sun has died and turned into a crystal of fading heat, the red dwarfs will still be shining. This makes them the most likely places to find life. By sheer numbers, most of the habitable real estate in the galaxy is parked around these little red stars. But there is a trap hidden in the math. Because a red dwarf is so cold, its habitable zone, the place where water is liquid, is tiny. To stay warm, a planet has to huddle dangerously close to the fire. It has to orbit closer than Mercury orbits our Sun. This proximity comes with a heavy price. Gravity takes hold. Just as the Earth has locked the Moon so that it always shows us the same face, a red dwarf locks its planets. The rotation stops. The planet becomes an eyeball world. On one side, the sun never sets. It is a scorched wasteland of eternal noon. On the other side, the sun never rises. It is a frozen hemisphere of eternal midnight. If life exists here, it clings to the thin strip of twilight between the two, a ring of perpetual sunset where the winds howl forever, from the hot side to the cold side. But the locking is not the worst part. The worst part is the temper of the star. Red dwarfs are unstable. They are prone to violent tantrums. Without warning, they can erupt with solar flares thousands of times more powerful than anything our sun produces. Because the planets are sitting right next to the star, they take the full force of the blast. Imagine a world that has spent millions of years building up an atmosphere and an ocean. Then, in a single afternoon, the star screams. A wave of X-rays and charged particles slams into the planet. It acts like a cosmic wind, stripping away the ozone layer, boiling the clouds and blasting the air itself out into space. We have looked at many of these worlds and found them bare. They are just rocks, sterilized by their own suns. This is the red dwarf trap. The most common parking spots in the galaxy might be the most deadly, and yet we keep looking. Because sometimes the conditions are just right. Sometimes we find a system so packed with worlds that it defies belief. A system where you could stand on one planet and see another one hanging in the sky, large enough to see the clouds with your naked eye. We are heading to the TRAPPIST system. 40 light-years away, in the constellation of Aquarius, sits a system that looks like it was drawn by a science fiction artist. It is called TRAPPIST-1. It is not just a star, it is a crowded room. Orbiting a tiny ultra-cool red dwarf are 7 planets. All of them are roughly the size of Earth. 3 of them sit squarely in the habitable zone. It is the highest concentration of rocky, potentially wet worlds we have ever found. But the numbers do not convey the magic of this place. The scale does. In our solar system, the planets are lonely. Mars is just a bright dot in our night sky. But the TRAPPIST system is miniature. The entire family of 7 worlds could fit inside the orbit of Mercury. They are packed together so tightly that they are practically touching in cosmic terms. Imagine standing on the surface of the 4th planet, TRAPPIST-1e. You look up. You do not just see a sun and moon. You see a solar system hanging over your head. The neighbouring planets would not be dots. They would be disks. Some would appear twice as large as the full moon looks from Earth. You could see their phases change by the hour. You could see the white swirls of their clouds, the blue of their oceans, and the yellow of their deserts, all with your naked eye. You could watch storms drifting across a world that is millions of miles away just by looking out your window. It is a sky filled with siblings, and there is a music to this system. The planets are locked in a gravitational dance called a resonance. For every 8 times the inner planet orbits, the next one orbits 5 times, the next one 3, and so on. They pass each other in a rhythmic beat that has kept the system stable for billions of years. It is a clockwork universe. If life started on one of these rocks, it could easily spread to the others. A simple asteroid impact could knock rocks full of microbes off one world, and they would fall gently onto the neighbour next door. We might find a system where all 7 worlds are alive, sharing the same biological heritage, watching each other across the narrow gap of space. TRAPPIST is a beacon of hope. It proves that the galaxy can be generous. But as we move inward, leaving the quiet suburbs of the galaxy and heading toward the centre, the rules change again. The stars get closer together. The radiation rises. The sky becomes bright enough to read by at night. We are leaving the safety of the rim. We are entering the chaotic, crowded and deadly downtown of the Milky Way. We are entering the Galactic Core. We live in the suburbs. Our sun orbits in a quiet, boring patch of the galaxy called the Orion Spur. Out here, the neighbours are polite. They stay light years away. The night sky is mostly black. But if we travel 26,000 light-years inward, the darkness dies. We are entering the Galactic Core. This is the downtown of the Milky Way, and it is a place of beautiful violence. As our ship approaches the centre, the stars stop being points of light. They multiply. They cluster. Finally, they merge into a single glowing fog. If you lived on a planet in the core, you would never see the universe beyond. You would never know that other galaxies exist. Your sky would be a blazing canopy of 1,000,000 suns, shining with the collective brightness of a full moon every single night. In the suburbs, stars are 5 or 6 light-years apart. Here, they are packed into the space of a few light weeks. They are so close that if one of them explodes, the shockwave doesn't just dissipate into the void, it strips the atmosphere off its neighbours. It is a cosmic shooting gallery. For life, this is nightmare. The radiation levels here are intense. The core is washed in a bath of X-rays and gamma rays from dying stars and pulsars. Any DNA that tried to evolve here would be shredded before it could learn to replicate. It is a spectacular light show, but it is sterile. And sitting in the centre of this fireworks display, governing the motion of every star in the galaxy, is the monster, Sagittarius A star. It is a black hole 4 million times heavier than our Sun. It is the anchor of the Milky Way. It is not a vacuum cleaner. It is a gravity well so deep that space and time are knotted around it. Stars here do not orbit in slow, lazy circles. They scream around the black hole at millions of miles per hour, whipped by the intense gravity. If we tried to take our ship too close, the tidal forces would not just crush us, they would spaghettify us. We would be stretched into a long, thin stream of atoms feeding the beast. So, while the core is the most energetic part of our home, it is likely a dead zone for biology. It is the engine room, not the passenger cabin. To find the next best place for life, we have to ride the waves that ripple out from the centre. We have to navigate the great spinning blades of the galaxy. We're entering the spiral arms. When we look at a map of the Milky Way, we see a beautiful swirling pinwheel. We see long, glowing arms wrapping around the core. It looks solid. It looks like a structure made of bone or steel, but it is an illusion. The spiral arms are not solid objects. They are not rigid spokes on a wheel. If they were, the outer stars would lag behind, and the arms would wind up tight until they disappeared. Instead, the arms are ghosts. They are waves of pressure moving through the galaxy, like ripples moving across a pond. Think of a traffic jam on a highway. The cars slow down, they bunch up, and then they speed up again. The jam itself stays in one place, but the cars flow through it. The spiral arms are cosmic traffic jams. As stars and gas clouds orbit the galaxy, they enter these invisible zones of high density. They get squeezed. And when you squeeze a giant cloud of gas, something violent happens. It ignites. The arms are the factories of the galaxy. This is where the pressure is high enough to crush hydrogen into new stars. If you could fly over a spiral arm, you would see it glowing blue. That blue light comes from massive newborn stars, monsters that burn hot and die young. Because they are factories, they are also graveyards. These massive stars do not live for billions of years like our sun. They live for a few million years, and then they detonate. They turn into supernovae. So the spiral arms are beautiful, but they are war zones. They are filled with the blinding radiation of birth and the shockwaves of death. For a civilization, passing through a spiral arm is a dangerous time. It is like steering a boat through a hurricane. The radiation spikes. The risk of a nearby explosion wiping out your ozone layer skyrockets. Our own sun passes through these arms periodically as it circles the galaxy. Some geologists believe that Earth's great mass extinctions coincide with the times we drifted into these dangerous neighbourhoods. We are lucky right now. We are drifting in the quiet space between two major arms in a little bridge called the Orion Spur. We are in the calm water, but to reach every habitable planet, we cannot stay in the calm water. We have to cross the arms. We have to dive into the traffic jam, endure the radiation, and navigate the minefield of exploding stars to reach the worlds on the other side. And once we cross them, the galaxy changes again. The crowd thins out, the bright blue stars vanish. The dust clears, we are heading toward the edge of the cliff. We are entering the lonely outskirts. As we leave the spiral arms, the traffic clears. The bright blue giants disappear. The dust clouds fade. We are travelling toward the edge of the map. This is the Galactic Rim. If the core is the city, this is the frozen tundra. Here, the stars are scattered far apart, drifting in solitude. The night sky from a planet here would be terrifyingly empty. On one side, you would see the Milky Way, a magnificent glowing wall of light cutting the universe in half. But if you turned your head, you would see nothing. Just the abyss. The true intergalactic void that stretches for millions of light years to Andromeda. Life out here faces a different problem than radiation. It faces starvation. To build a planet like Earth, you need heavy ingredients. You need iron for the core, silicon for the rocks, oxygen for the water, and carbon for the life. These elements are cooked inside massive stars and scattered when they explode. The core and the spiral arms are rich in these ingredients because generations of stars have lived and died there, enriching the soil of space. But the outskirts are poor. The stars here are ancient and pristine. They are made almost entirely of hydrogen and helium, the simple gas of the Big Bang. There has not been enough recycling here to create the heavy dust needed to build rocky worlds. So, while the stars here are safe from supernovae, they are often lonely. They might not have planets at all. Or if they do, they might be gas giants, lonely Jupiters floating without a solid surface to stand on. This creates a concept scientists call the Galactic Habitable Zone. It is a ring of life. You cannot be too close to the centre, or the radiation kills you. You cannot be too far at the edge, or you cannot build a planet to stand on. We live in the sweet spot, the Goldilocks zone of the galaxy itself. But rare does not mean zero. Even in the metal-poor wasteland of the Rim, there will be anomalies. There will be systems that manage to scrape together enough dust to build a home, and a civilization born there would be the loneliest in the galaxy. They would look out at the universe and see the great spiral of the Milky Way not as a home, but as a distant object in the sky. If we reach these outer limits, we have conquered the geography of the galaxy. We have touched the core, the arms, and the rim. We have the map. But a map is useless if you do not have the time to travel it. We still have the problem of scale. Even with fusion, even with antimatter, one ship cannot visit 300 million worlds. There is simply too much ground to cover. To truly fill the galaxy, we do not need a faster ship. We need a ship that can copy itself. We need to stop acting like explorers and start acting like a virus. We are about to enter the era of the von Neumann machine. We have established that the galaxy is too big for a single fleet. Even if we built 1,000 starships, or 1,000,000, it would take eons to visit every world. To conquer the scale of the Milky Way, we have to stop thinking like explorers. We have to start thinking like a virus. This is the concept of the von Neumann machine. Named after the mathematician John von Neumann, this is a ship designed with one primary directive: to reproduce. Imagine we send out just one probe. It is not very big, and it carries no humans. It is an autonomous factory controlled by an artificial intelligence. It crosses the void to the nearest star, say Alpha Centauri. It finds an asteroid, or a small moon. It lands. It does not plant a flag. It starts to eat. The probe mines the raw materials: iron, carbon, silicon. It builds solar collectors to gather energy. It builds smelters and refineries. And then it uses those materials to build copies of itself. Maybe it takes 10 years. Maybe it takes 100. But eventually, the mother probe launches 2 daughter probes. They are identical to the first. They fly off to 2 new stars. The original probe stays behind to monitor the system, while the daughters repeat the cycle. 2 ships become 4. 4 become 8. 8 become 16. This is the power of exponential growth. It is the same math that allows a single bacteria to fill a petri dish in a day. At first, the progress looks slow. You might not notice it for thousands of years. But once the curve turns upward, it becomes an explosion. If these probes travel at just 10% of the speed of light and take 500 years to replicate at each stop, the math says they could visit every single star in the Milky Way in just 10 million years. 10 million years sounds like an eternity to us. But the galaxy is 10 billion years old. In the lifetime of the Milky Way, 10 million years is a blink of an eye. It is a single afternoon. This means that a civilization does not need warp drive to fill the galaxy. They do not need wormholes. They just need patience and a machine that knows how to copy itself. Once you press the start button on the first probe, the process becomes unstoppable. It is a shockwave of metal and silicon expanding outward, eating asteroids and cataloguing worlds until it hits the edge of the rim. We could do this. The technology is not magic. It is just advanced robotics. We could arguably launch the first seed within a century. But this creates a terrifying paradox. If it is so easy, if a single civilization could carpet the galaxy in a geological heartbeat, then why hasn't it happened? Why aren't there von Neumann machines eating our asteroid belt right now? And if we do launch them, we create a new problem. We will have eyes on 1 billion worlds. We will have an empire of machines stretching from the core to the rim. But how do we control it? How do you issue a command to a probe that is 50,000 light-years away? We are about to discover that in a galaxy-spanning empire, the internet is broken. We live in an age of instant gratification. If you send a message to a friend in Tokyo, they read it a second later. We're used to the world feeling small. We assume that a future galactic civilization will feel the same, that we will have a galactic internet where we can video chat with colonies on the other side of the Milky Way. Physics says no. The speed of light is not just a speed limit for ships, it is a speed limit for information. Nothing, not radio waves, not lasers, not even a subspace signal from science fiction, can go faster than light. This creates a lag that shatters the idea of a unified empire. Let us look at the numbers. If we establish a colony on Proxima Centauri, 4 light-years away, the internet connection is terrible. If you say hello, you have to wait 4 years for your voice to reach them, and another 4 years for their answer to come back. An 8-year pause in conversation. You cannot have a war room, you cannot have a stock market, you cannot have a president who gives orders. But that is just the neighbour. If we send a signal to the other side of the galaxy, to the colonies on the far rim, the delay is 100,000 years. Think about that. If a crisis happens, a plague, a rebellion, an alien attack, and they send a distress signal, that message will travel through the dark for 1,000 centuries. By the time it reaches Earth, the civilization that sent it will likely be dust. The humans who receive it will have forgotten the colony even existed. This means the galactic internet is not a network. It is an archive. It is a history book that is always out of date. A galaxy-spanning civilization is not a single organism. It is a collection of lonely islands. Each system is isolated by a wall of time. The colonies will be on their own. They will have to solve their own problems, fight their own wars, and write their own laws. Earth cannot help them. Earth cannot even hear them. This isolation breaks the human connection. We are social animals. We rely on shared culture, shared news, shared reality to feel like us. But across these distances, us stops existing. If a colony is left alone for 10,000 years, cut off from the motherland, they stop being a colony. They stop being Earthlings. They start to drift. Their language shifts. Their values change. Even their bodies might begin to adapt to their new home. We are not just spreading humanity across the stars. We are shattering it into 1,000 different pieces, and given enough time, those pieces will become strangers to one another. We are about to see the drift of culture turn into the drift of species. When we imagine the future, we imagine a federation. We picture a united Earth Navy where everyone wears the same uniform, salutes the same flag, and speaks the same language. But biology tells us that this is a fantasy. The galaxy is not a melting pot. It is the Galapagos Islands on a cosmic scale. When you isolate a population on an island and cut off contact with the mainland, they stop being the same species. They adapt to the local food, the local predators, the local weather. Over time, they drift. Now, apply that to the stars. Imagine a colony settled on a heavy world, a planet with gravity twice as strong as Earth. The first generation will suffer, their backs will ache, their hearts will struggle, but their children will adapt. Over 1,000 years, natural selection will sculpt them. They will become shorter. Their bones will become dense and thick like concrete. Their muscles will be corded and powerful. If they met a human from Earth, they would look at us as tall, fragile willows, ready to snap in a stiff breeze. Now imagine a colony on a low-gravity moon, or living permanently in zero-G orbital habitats. They would grow tall and slender. Their bones would be light. Their toes might lengthen into fingers to grasp rungs with their feet. We will not look like the same species anymore, and we won't think like the same species either. Language changes faster than biology. Read a book from 500 years ago and it feels strange. Read a book from 1,000 years ago and it is a foreign language. If a colony is cut off for 10,000 years, they will not speak English, or Mandarin, or Spanish. They will speak something new, a language born of their world, filled with words for weather we have never felt and colours we have never seen. Their myths will change. Earth will stop being a home and start being a legend. They might forget that they came from the sky at all. They might believe they were created there on that rock by a local god. This is the beautiful, terrifying truth of the journey. We set out to find aliens, but in the process of filling the galaxy, we will become the aliens. If you could fast forward 5 million years and look at the Milky Way, you wouldn't see humanity. You would see 1,000 different species all sharing a common ancestor, but utterly unable to understand one another. Some will be flesh and blood, some will be silicon and steel, some might be pure consciousness uploaded into the cloud of a Dyson swarm. We are seeding a garden that will grow wild. But this brings us back to the most haunting question of all. If biology drifts, if expansion is natural, and if the galaxy is old enough for this to have happened 1,000 times before, where are they? If a single civilization can spread across the stars in just a few million years, the Milky Way should be teeming with life. It should be noisy. It should be crowded. But when we point our telescopes at the habitable worlds, we don't see cities. We don't see ships. We see silence. We are about to confront the Fermi paradox, and the answer might be that we are walking into a graveyard. We have just proven that a single civilization could fill the Milky Way in 10 million years. That sounds like a long time to a human, but to a star it is a heartbeat. The galaxy is 13 billion years old. Do the math. If a civilization started expanding when the galaxy was young, say billions of years ago, They should have finished the job eons before the first dinosaur walked on Earth. Every star should have a flag on it. Every asteroid should be mined. The night sky should not be dark. It should be buzzing with the heat waste of a billion machines. But when we look up, we see a pristine wilderness. We see stars burning fuel they have held for billions of years, untouched. We see clouds of gas drifting idly, unharvested. We listen for radio waves, for laser pulses, for the hum of engines, and we hear static. This is the silence we should not hear. It is the loudest noise in science. Think of it like walking into a mansion. The lights are on, the table is set for dinner, the food is steaming hot, but there is no one there. You walk from room to room, expecting to find the owners, but every room is empty. You check the garden. Empty. You check the basement. Empty. Eventually you have to ask, are we the first ones to arrive, or did something happen to the people who were here before? There are only two possibilities, and both are terrifying. The first possibility is that we are alone. That life is so impossibly rare that in a galaxy of 400 billion stars, we are the only ones who made it to the stage of building rockets. We are the first awake in a sleeping house. This makes us precious. It means we carry the only torch of consciousness in the dark. If we extinguish ourselves, the galaxy goes blind again. The second possibility is that we are not alone. The mansion is full, but we cannot see them. Maybe they are like uncontacted tribes in the Amazon, and the galaxy is a nature preserve. Maybe the aliens are watching us right now, hidden behind a prime directive, waiting for us to grow up. Or maybe they have evolved beyond matter entirely, living in the databanks of black holes, ignoring the primitive monkeys playing with firecrackers on Earth. But there is a third option, a darker one. Maybe the mansion is empty because everyone who tries to live there dies. Maybe there is a trap hidden in the development of life, a hurdle so high that no one clears it, a filter that wipes civilizations out just as they are getting ready to leave their cradle. We are about to discuss the Great Filter. And we have to ask ourselves, is the trap behind us, or is it waiting just ahead? The Great Filter is the scariest theory in science because it turns hope into fear. It suggests that there is a step in the evolution of life that is almost impossible to cross. A wall that stops dust from turning into starships. The question is, where is the wall? There are two possibilities, and one of them spells our doom. Scenario 1, the filter is behind us. Maybe the hard part was the beginning. Maybe the universe is full of dead rocks because turning simple chemicals into the first spark of life is incredibly rare. It might be a lottery that only happens once in a trillion galaxies. If this is true, we are the lucky winners. We have already climbed the mountain that no one else could climb. We are unique, we are safe, and the galaxy is ours for the taking. But then there is scenario 2. The filter is ahead of us. Maybe life is easy. Maybe slime and bacteria grow on every wet rock in the Milky Way. Maybe even intelligence is common. But perhaps there is a trap waiting for civilizations once they get smart. Think about it. As soon as a species learns to split the atom, build a computer, or change its own climate, it enters a danger zone. We have only had dangerous technology for 80 years. In galactic time, that is a microsecond. If the filter is ahead, it means that every civilization that reaches our level eventually destroys itself. They blow themselves up, or they poison their atmosphere, or they create an artificial intelligence that wipes them out. They flare up like a match in the dark, and then they burn out before they can build a colony ship. This leads to a terrifying conclusion. We usually hope to find life on Mars. We want to find a fossil of a bacteria or a swimming microbe under the ice of Europa. It would be the greatest discovery in history. But if the Great Filter theory is right, finding alien life would be the worst news imaginable. If we find life on Mars, it means life is easy to start. It means the filter is not at the beginning. It means the trap is waiting for us in the future. The more common life is, the more likely it is that we are walking toward our own extinction. We are walking a tightrope. We want to believe we are special, but not too special. We want to believe the galaxy is empty because we are the first, not because we are the last survivors of a universal slaughter. But let us assume we survive. Let us assume we pass the test. What happens when we finally cross the void? What happens to the sky above our heads as we leave the Earth behind? We are about to look at the constellations one last time, because as we travel, the stars themselves are going to move. We grow up thinking the sky is a wallpaper pasted on the ceiling of the world. We look up and see the Big Dipper pouring its imaginary water. We see Orion the hunter raising his shield against the bull. We see the North Star, the unmoving anchor of the Northern Hemisphere. We use them to navigate our ships, plant our crops, and tell our children stories. They feel permanent. They feel like they belong to us, a fixed heritage passed down from the Stone Age to the Space Age. But the moment we leave the solar system, we realize that a constellation is a beautiful lie. It is a trick of perspective, a flat drawing made of deep space. The stars in Orion look like they're standing next to each other, locked in a formation, but they are strangers. One star might be 10 light-years away, a close neighbour, while the one right next to it in the drawing is a supergiant burning 1,000 light-years deep in the background. They have no relationship to one another. They only form a shape because we are standing in exactly the right spot in the galaxy, a tiny viewing platform called Earth, to see the lines connect. As our ship moves away from Earth, the picture falls apart. Imagine walking around a statue. From the front, it looks like a hero. From the side, it is just a lump of stone. From the back, it is unrecognizable. The galaxy is that statue, and we are finally stepping off the viewing platform. As we travel to Alpha Centauri, the distortion begins. It starts slowly. The familiar shapes simply look wrong. The belt of Orion snaps in half. The hunter loses his shoulders. The Big Dipper stretches and twists until it looks like a random scatter of sparks, its ladle bent beyond recognition. The Southern Cross, the guide for centuries of sailors, dissolves into a meaningless triangle. For the crew on the ship, this is not just a geometry lesson. It is a profound psychological loss. They can no longer look out the window and find the North Star. The compass of human history is broken. The zodiac, the myths, the astrological signs, they all evaporate. The crew is entering a sky that has no names, no stories, and no history. They are drifting into a wilderness where the landmarks have been erased. But it is not just distance that breaks the sky. It is time. We often forget that the galaxy is not a static painting. It is a carousel. It is a fluid structure. Every star is moving, drifting, and bobbing in its own lane. Our sun is orbiting the galactic core at 500,000 miles per hour, dragging the planets with it. As we travel for centuries or millennia to reach the far colonies, the galaxy is actively rearranging itself around us. Consider Barnard's star, a faint red dwarf near us. It is currently sprinting through our neighbourhood like a bullet, moving faster across our sky than almost any other star. In 10,000 years, it will be in a completely different constellation. Proxima Centauri will drift away from its partners, breaking up the triple star system of Alpha Centauri. By the time our descendants reach the other side of the spiral arm, the sky of Earth will be gone. The constellations of 2024 will be unrecoverable, scattered by the wind of galactic rotation, and the most terrifying realization is looking back. If the travelers try to find home, they will face a wall of anonymity. From 1,000 light-years away, the sun is not a blazing furnace. It is a dim, yellow dwarf, indistinguishable from billions of other yellow dwarfs. It does not stand out. It has no beacon. Even if they had a telescope powerful enough to look back at the coordinates where Earth should be, they wouldn't be able to find it without perfect records. Home becomes just one nameless yellow dot, lost in a sea of nameless yellow dots. This forces the colony to start over. They will have to draw new lines on the night sky. They will invent new heroes and new monsters to connect the stars of their new home. They will look up at a night sky that would terrify us, a sky of strange geometries, bright nebula clusters we cannot see from Earth, and alien bright spots that cast shadows at midnight. And as the sky changes above us, so does the ground beneath our feet. We must remember that while we are out there conquering the galaxy, freezing ourselves in time, our home is aging. Earth is not eternal. The planet we left is not the planet that exists today. We're about to look back at the pale blue dot and realize it might not be blue anymore. There is a comfortable lie we tell ourselves, a myth that sits at the very foundation of our psychology. We believe that no matter how far we roam, we can always come home. We think of Earth as the eternal safe harbour, the unshakable bedrock of our existence that will be waiting for us with blue skies, green hills, and cool rains whenever we decide to turn the ship around. But if we are truly talking about a galactic timescale, Earth is not a harbour. It is a sinking ship. The problem is the sun. We tend to think of the sun as a steady, unchanging friend, a battery that never runs out. But stars are living things, they have metabolisms, they evolve, and the specific pathology of our star is that as it ages it gets brighter. It burns its fuel faster and faster, accumulating helium ash in its core, which forces the nuclear furnace to burn hotter to maintain equilibrium. Every billion years the sun becomes about 10% more luminous. That does not sound like much. To a human, 10% is a rounding error, but to a delicate, balanced biosystem like Earth, it is a death sentence. Most people believe the Earth will die when the sun turns into a red giant, swallowing us in fire 5 billion years from now. That is the story we're told in school, but that story is wrong. The end comes much, much sooner than that. Long before the sun swells up to physically touch us, it will destroy us with heat. In about 600 million years, roughly the time it takes for our galaxy-spanning civilization to fully mature, the sun will cross a critical threshold. The extra energy hitting our atmosphere will trigger a cascade of chemical reactions that cannot be stopped. It starts with the rocks. As the planet heats up, the weathering of silicate rocks accelerates. This chemical process scrubs carbon dioxide out of the atmosphere. Paradoxically, while we worry about too much CO2 today, the future death of Earth will be caused by too little. The levels will drop so low that photosynthesis becomes impossible for most plants. The forest will be the first to go. The great green canopy that has covered the continents for eras will turn brown and crumble. With the death of the plants, the oxygen production stops. The food web collapses from the bottom up. Animals will suffocate in a thinning atmosphere, starving in a world of dead wood. Then, the water goes. As the temperature continues to climb, the oceans will not just recede, they will destabilize. We will enter a moist greenhouse state. Water vapor is a potent greenhouse gas, far worse than carbon dioxide. As the oceans evaporate, they thicken the air, trapping more heat, which causes more evaporation. It is a runaway feedback loop. The stratosphere will become saturated with water. There, the harsh ultraviolet light from the sun will smash the water molecules apart, stripping the hydrogen away and blasting it out into space. We won't just lose the liquid, we will lose the atoms themselves. The oceans will bleed away into the void, leaving behind only salt and dry, cracked basins. Earth will stop looking like the blue marble. It will turn into a blinding white ball of clouds, trapping the crushing heat below, baking the surface until the continents are sterile deserts of salt and basalt. Our home will become a twin of Venus, a pressure cooker where lead melts on the ground and the wind screams through a toxic, superheated haze. This is the hard truth of the timeline. By the time our descendants reach the far side of the Milky Way and turn their telescopes back toward the Orion Spur, Earth will be a graveyard. If they try to visit the cradle of humanity out of nostalgia, they will not find a monument. They will find a hellscape. The museums, the cities, the ruins of our history, everything we ever built, every book we ever wrote, every bone we ever buried, will have been erased by the wind and the fire. The tectonic plates might grind to a halt as the water that lubricates them vanishes. The planet will be a silent, dead rock, sterilized by the very star that gave it life. This changes the fundamental meaning of the mission. We are not leaving Earth because we are curious. We are leaving because we are refugees in waiting. The galaxy is not a playground for tourists. It is a lifeboat. If we stay here, we die. The only way for the human story to continue is to carry the seed of life to a new pot before the old one shatters. We are racing the clock of stellar evolution, and that clock has no pause button. But as we spread out, we will realize that planets are fragile things. They are easily broken. They are vulnerable to asteroids, to climate shifts, and to the temper of their parent stars. To truly survive for eternity, to survive the death of stars and the decay of worlds, we need to stop living on the crumbs of energy that fall on planetary surfaces. We need to go to the source. We need to stop just looking at stars and start eating them. For all of human history, we have been scavengers. We are biological machines that crawl across the surface of a rock, digging for scraps. We dig coal out of the ground, which is just fossilized sunlight from millions of years ago. We pump oil from the sand, desperate for the chemical energy stored in dead algae. Even now, with our most advanced technology, we put up solar panels to catch the tiny leftover crumbs of sunlight that happen to fall on our roof. We fight wars over these resources because they are scarce. Our entire economy, our politics, and our survival strategies are built on the premise that there is not enough to go around. We live in a world of limits, But the moment we leave the atmosphere, we realize that scarcity is an illusion. The universe is not poor, it is embarrassingly rich. We just haven't learned how to open the vault. Look at the sun. It is not just a bright light. It is a fusion engine of terrifying scale. Every single second, it burns 600 million tons of hydrogen. It converts matter into energy with an efficiency that makes our nuclear power plants look like steam engines. It releases an amount of energy so vast that it defies language, more energy in 1 second than humanity has used in its entire existence, from the first campfire to the latest rocket launch. It screams power into the void in every direction. And what do we do with it? Earth is a tiny speck orbiting 93 million miles away. Geometrically, we are insignificant. Imagine a sphere of energy expanding outward from the sun. By the time that sphere reaches Earth, we occupy such a microscopic fraction of the surface area that we catch less than 1/1000th of the sun's output. The rest of it, 99% misses us completely. It flies past our planet, racing into the dark, and is lost forever in the deep cold of space. It is a waste on a galactic scale. It is like lighting a massive bonfire to read a book, and then sitting 10 miles away with a pair of binoculars, trying to catch the glow. When we become a true spacefaring civilization, this waste will become offensive. We will look at a star and we won't see a pretty light in the sky. We will see a nuclear reactor that is venting its fuel into nowhere. We will see a leaky faucet gushing liquid gold into a drain. This realization marks the beginning of the era of starlight. It is the moment we stop hunting for energy and start harvesting it. We will realize that planets are not the prize. Planets are just the debris left over from the main event. They are gravity traps where energy goes to die. The star is the prize. A civilization that understands this crosses a threshold. They move from a Type 1 civilization, masters of a planet, to a Type 2 civilization, masters of a star. They do not need to fight for resources. They have access to more energy in a single day than a planetary civilization uses in 1,000,000 years. With that kind of power, the definition of impossible changes. You don't just travel the galaxy, you reshape it. Consider terraforming. With planetary energy, terraforming Mars is a struggle of centuries, trying to thicken the atmosphere with factories. With stellar energy, you simply build massive orbital mirrors the size of continents. You reflect the raw power of the sun onto the Martian polar ice caps, melting them in a week. You can steer asteroids to crash into worlds to add water. You can build lasers powerful enough to push solar sails to relativistic speeds, not just for small probes, but for massive colony ships. We could build factories that churn out antimatter not by the gram, but by the ton, giving us the fuel to reach the other side of the Milky Way. We could run computer simulations so complex that they could model the entire history of the human race in real time. We can stop worrying about survival and start thinking about creation. This is the graduation test for a species. To pass, we have to stop clinging to the rocks where we were born. We have to move our industry, our homes, and our future off the surface of planets and into the space around the star. We have to get closer to the fire, but you cannot harvest a star with a solar panel. You cannot catch a tsunami with a bucket. To capture the full output of a sun, you need engineering on a scale that makes the pyramids, the Great Wall, and the skyscrapers of New York look like sandcastles built by children. You need to build something that surrounds the star completely. You need to catch every photon before it escapes. We're about to build the ultimate megastructure. When science fiction writers first imagined capturing a star, they pictured a solid shell. They imagined a giant hollow ball of steel built around the sun, completely enclosing it like an eggshell. They called it a Dyson sphere. It is a beautiful image, a symbol of ultimate protection and mastery, but physics hates it. A solid shell that big is mechanically impossible. There is no material in the universe strong enough to hold it together. The gravitational stress of the star would tear the steel like wet paper, and the entire structure would shatter and crash into the inferno. A rigid sphere is a tomb, not a home. So, we will not build a sphere. We will build a swarm. Imagine billions of satellites, solar collectors, mirrors, habitats, and factories, all orbiting the sun in a dense buzzing cloud. They are not connected by beams or girders. They float independently, orbiting in precise paths like a flock of birds or a swarm of bees. Individually they are small, but there are so many of them, quadrillions of them, that from a distance they look like a solid fog. This is the Dyson swarm. It captures the light, turns it into electricity, and beams it wherever we need it, without fighting the laws of gravity. But to build a cloud of machines that can block out a star, we need material. We need more metal, glass, and silicon than we have mined in the entire history of the human race. We cannot launch this material from Earth. The gravity well is too deep. We have to find it in space, so we will have to make a sacrifice. We will choose a planet to die so the swarm can live. The most likely candidate is Mercury. It is a dead rock, rich in iron and heavy metals, sitting conveniently close to the sun where solar power is intense. We will fly there. We will land self-replicating mining robots, and we will dismantle it. We will not just mine Mercury, we will eat it. We will peel it apart layer by layer, turning its mountains into mirrors and its core into computer chips. We will launch this material into orbit using electromagnetic railguns powered by the sun itself. The process is exponential. The first set of mirrors we build will provide the energy to mine faster, which lets us build more mirrors, which gives us even more energy. It is a runaway feedback loop. In just a few decades, Mercury will be gone. In its place will be a shimmering cloud of glass and metal spreading out to embrace the sun. When the swarm is complete, humanity changes. We undergo a fundamental shift in our nature. We are no longer a species that lives on the surface of a ball clinging to the crust like moss. We become a species that lives in the atmosphere of a star. The living space created by a Dyson swarm is staggering. If we built rotating habitats among the solar collectors, spinning them to create gravity, we could create a livable surface area equivalent to 1 million Earths. We could have 1 trillion people living in comfort, with endless energy, bathing in the raw light of the sun, with the rest of the galaxy just a shuttle ride away. But to an outsider looking at our solar system from deep space, something frightening would happen. As we add more and more collectors, we block more and more light. The sun would start to dim, it would turn red, then deep crimson. Eventually it might vanish entirely. A fully completed Dyson swarm hides the star. The visible light is trapped inside, used to power the machines and grow the crops. The only thing that leaks out is heat, weak infrared radiation. To an alien astronomer, our solar system would look like a dark, warm ghost. The star would be visually gone, replaced by the heat signature of a colossal machine. This is the ultimate camouflage, and it is also the ultimate weapon. With the power of a Dyson swarm, we don't just launch ships, we launch beams. We can use the entire energy output of the sun, not just a fraction, but all of it, to power immense lasers. We can push starships to relativistic speeds in days rather than years. We can create highways of light that span the void, and if we needed to, we could turn that power outward. A civilization with a Dyson swarm can fire a laser that could melt the surface of a planet light years away. We become a Type 2 civilization. We become the masters of our own gravity well, invincible in our own home. And once we have conquered one star, the rest is just repetition. We send the fleet to the next star, build a swarm and move on. Star by star, the galaxy goes dark. We are approaching the end of the journey. We have travelled for millions of years. We have colonised the habitable worlds, and we have wrapped the stars in metal. Now, it is time to look at the finished map. It is time to see the garden of the Milky Way. We began this journey on a single rock, terrified of the silence. We looked up at a sky that felt empty, wondering if we were the only eyes watching the stars. We spent millions of years crossing the bridges of light, enduring the cold, paying the price of time and sacrificing entire generations to the void. But now, the work is done. The long silence is broken. If you could float above the plane of the Milky Way today, eons after our departure, you would not see the same galaxy that we see tonight. The wilderness is gone. The dark forest has been cut down, and in its place we have planted a garden. The visual transformation is absolute. In the era of the natural galaxy, the spiral arms were defined by the chaotic blue light of short-lived stars and the dark smog of dust lanes. In the era of the civilized galaxy, the light is ordered. The chaotic, wasteful burning of stars has been tamed. Every habitable world we identified, all 300 million of them, is now a home. But we didn't stop at the planets. We moved into the vacuum itself. The red dwarf systems, once seen as dangerous traps, are now the stable power grids of the Empire, their flares harvested to run computations that simulate entire universes. The spiral arms are no longer minefields of radiation, they are highways of laser light, pushing cargo between stars at relativistic speeds. To an outside observer, the Milky Way no longer glows with the harsh white light of fusion. It glows with the warm infrared hum of Dyson swarms. It looks less like a fire and more like a city seen from an airplane at night. A vast, deliberate structure of glowing nodes and connecting lines. The great silence that frightened us in the beginning has been replaced by a chorus. The galaxy hums. It does not hum with the noise of machines, but with the data of existence. It hums with the radio traffic of 1 trillion civilizations, all born from the same terrestrial seed, yet wildly different in their bloom. They are the children of the long sleep, the survivors of the radiation, the architects of the gravity wells. Some are biological, retaining the shape of the humans who left Earth, living in domed paradises on terraformed worlds. Others are beings of steel and silicon swimming through the vacuum of space, feeding directly on solar wind. Some have abandoned bodies entirely, uploading their consciousness into the diamond banks of computer clouds orbiting black holes. They speak 1 million different languages. They live in realities we cannot comprehend. But they are all us. They are the divergence of the human story, spreading out to fill every available niche in the cosmos. We have turned the Milky Way into a single living organism. The trade routes are its arteries. The communication networks are its nerves. Information flows from the core to the rim, binding the galaxy together in a web of shared history. This was the answer to the paradox. We asked, where is everybody? And the universe answered with silence. It wasn't ignoring us, it was waiting for us. It was waiting for us to become the everybody. It was waiting for life to wake up, leave the cradle, and take the reins of stellar evolution. But this victory comes with a solemn realization. We did not conquer the galaxy to own it. We conquered it to save it. The universe is dying. It has been dying since the Big Bang. Slowly, inexorably, the stars are burning out. Entropy is the ultimate enemy, the cold wind that seeks to blow out the candle of complexity. A natural galaxy is a machine that wastes energy, burning its fuel in a glorious but brief flash before fading into eternal darkness. By spreading out, by harvesting the energy of the stars and protecting the flame of consciousness, we have bought ourselves time. We have become the stewards of the light. We can manage the burn rate of stars, extending their lives by billions of years. We can hoard energy against the coming cold. We have ensured that no single asteroid, no single plague, no single war can ever extinguish the human story. We have made ourselves immortal, not as individuals, but as a phenomenon. As long as there is a star burning in the Orion Spur, or a black hole spinning in the core, someone will be there to see it. Someone will be there to think, to feel, and to remember that we once began on a small blue world. So, tonight, when you go outside, look up. Look at the band of the Milky Way stretching across the dark. Do not see it as a void. Do not see it as a lonely abyss that doesn't care about you. See it as a map of potential. See it as a construction site. See it as a promise. The stars are not just nuclear fire, they are destinations waiting for their names. The silence is not a sign of emptiness. It is a canvas waiting for us to paint upon it. The journey will be long. It will be harder than anything we have ever done. It will demand everything from us. But we have the ships in our minds, we have the physics in our equations, and we have the will in our blood. The gate is open, the garden is waiting. Thank you for taking this journey with me.